Hello everyone, in this video we're going to learn about an extremely powerful tool in evaluating both indefinite and definite integrals, okay? And that is basically, let's explore, okay, before we get into the actual names. So when would you do this, okay? So let's say you're given this extremely complicated looking integral, okay? We want to find, let's use black. I want to find the integral of, say we want to find the integral of 3x to the 5th plus 2x cubed let's get some better numbers. Let's do 5x to the 4th plus 7x to the 6th times x to the 5th plus x to the 7th to the 10th power dx. Okay, so this is an extremely complicated looking integral. Okay, so how would you even begin to evaluate this? Because me personally, I do not have enough time to multiply this product out. Okay, however, if you notice the function and its derivative in the same place, okay, if you see them right next to each other, you can apply something known as U-Substitution, which is an extremely powerful and efficient way to evaluate messy integrals such as this. Okay, so if you were to, so let's not expand this out and use U-Substitution. And U-Substitution can basically be, you can basically define it as the reverse chain rule or the inverse chain rule. Whatever you want to call it, I'll call it the reverse chain rule because it deals with composite functions, okay? So what happens if, let's say we define a variable u, and u is the most common variable for this, why we call it U-Substitution. Let's say we define u as x to the 5th plus x to the 7th, okay? And so what we want to do is turn this messy integral into a much simpler integral in terms of a different variable, okay? And if we introduce u as x to the 5th plus x to the 7th, and the reason why this works when the derivative is right next to it, okay, is because du dx, we take the derivative with respect to x of u, that equals 5x to the 4th plus 7x to the 6th. Or du is equal to 5x to the 4th plus 7x to the 6th dx, right? So this is u, and this is du. Okay, we have 5x to the 4th plus 7x to the 6th times dx. So we're basically rewriting the integral in terms of u. Okay, and if we rewrite the integral by making these substitutions, look what we get. U to the 10th du. And now this is a much simpler, much simpler integral to evaluate. Okay, because we can basically use our reverse power rule. U to the 11 over 11. But remember, we have to, so let's put plus c, okay? But remember, we have to change u back to x, okay? Since our original integral was looking with an integral with respect to x, our integration variable was x. So let's turn this back into x. So u was x to the 5th plus x to the 7th. So you can substitute back x to the 5th plus x to the 7th, to the 11th over 11 plus c. Okay, this is not that difficult. Okay, it's not that difficult. Let's do another one. Let's try the integral of 3x squared times the square root of x cubed plus 1 dx. And if you had practice with derivatives a lot, you can see that 3x squared is the derivative of x cubed. However, we can just as easily define u, we have to pick our u, as x cubed plus 1. Okay? And the derivative with respect to x, du dx, equals 3x squared, and 1's a constant. So du equals 3x squared dx. So we substitute all the necessary variables. This is du, and this part, x cubed plus 1, will be u. So we rewrite the integral to be the square root of u du. And if you take that integral by turning into a fractional exponent and applying the inverse power rule on it, you would get 2 over 3 times u to the 3/2 power, and substitute back, we get 2 over 3 times x cubed plus 1 to the 3/2 power plus c, okay, which you can rewrite as 2 over 3 times the square root of x cubed plus 1 cubed plus c. This is our integral. Now, it's not always this easy, okay? So, not all integrals have convenient derivatives. However, knowing what to substitute in is basically a challenge, okay? So, let's do one more of these simple ones, okay? Just so we can get accustomed to the notion of what U-substitution is. So 5 cosine of 5x dx. Now, it should be apparent what u should be. U should be 5x. Why? Because the derivative of u, so derivative of 5x, is 5. And you can easily see a 5 right over here, and a dx. Okay, so du dx is 5. So du equals 5 dx. Which is why if you spot a u quickly, you don't have to do a lot of, as you get better, you get to spot the u quickly. You get to spot these patterns. And now we get the integral of cosine of u du. Okay? And we get sine of u du. Okay, we're integrating with respect to u until we substitute back in. And we get sine of 5x plus c. Now, not everything is this perfect, unfortunately. Okay? Let's look at this function. Let's look at this function. What about x times the square root of x cubed plus 1? So very similar to an integral that we did in this video, except x squared is missing its coefficient. Okay? And this serves to be a problem, because if we let u equal to x cubed plus 1, as we did previously, then du dx is 3x squared. And we don't have a 3 anywhere. So in order to get a du, we have to have a 3x squared and a dx. We have a dx and x squared, but not a 3. So what can we do? What do you think we should do? Well, why don't we introduce a 3? Okay, in other words, why don't we divide and multiply by 3? Okay, so that effectively does not change the value of the integral. It still maintains equality since 3 divided by 3 is 1. Okay, so we're essentially multiplying it by 1. But by multiplying by 3 over 3, this 3 can combine with this x squared. And now you have your du, which means you can substitute here for u. So you could pull out this. So you have 1/3 times the integral of the square root of u du. And that equals 1/3 times the 2/3 u to the 3/2 power, u to the 3/2 power plus c. Now we have to substitute back in our original expression for u in terms of x. So we have 2/9 multiplied to fractions times the square root, sorry, in radical form, of x cubed plus 1 cubed. Okay, plus c. And now that you know that if you multiply and divide by the same number, U-substitution is now showing how powerful of a tool this actually is. Okay? With U-substitution, messy integrals such as this, you can't really evaluate with the power rule. Okay? So by using U-substitution, turning it into an integral with a different variable, much simpler integral, and substituting back, you now open the range of functions of which you can integrate. Okay? So let's do one more. Let's do a couple more. So let's do this. Okay, let us do this integral. So why not we do this? The integral of x squared over 1 plus x cubed squared dx. So what do you do over here? Okay, so what now? Well, what I think is a good idea is you have an x squared and an x cubed. So I think some u substitution would suffice. How? By letting u equals 1 plus x cubed. So du is equal to 3x squared dx. So we're basically finding du dx, which is 3x squared, multiplied by dx. Okay? Now, we don't have a 3x squared dx, but we do have an x squared dx. So we can introduce a 3 by multiplying and dividing by 3 at the same time. And now we have our conditions for du and our condition for u. So now we can carry out with u substitution. Okay, by having 1 over u squared du, or the indefinite integral of u to negative sec 2 power times du. And if we do this integral, okay, if we do this integral, you would get -1 times u to the negative 1, or just negative 1 over u. Right? So we get negative 1 over u, but remember we have to back substitute. We have to substitute back our original expression. So it's negative 1 over 1 plus x cubed plus c. Okay, and the reason I'm doing so many of these indefinite integrals is that definite integrals are basically indefinite integrals, but you would evaluate them by finding indefinite integrals and using the first fundamental theorem. Okay? However, there is an important quirk about indefinite integrals, which I will get later in the video. Okay? Now, let's look at something like this. This integral is a little bit trickier. X times the square root of 2x minus 1 dx. This integral is a bit tricky, okay, because you have an x outside and inside the integral. So it seems like U-substitution cannot work. However, what you might not realize is that the derivative is hidden. So if let's make u equal to 2x minus 1. Let u equals 2x minus 1. So what's du dx? Du dx is 2. So du equals 2 dx. Now, we only have a dx, okay? So it's kind of a problem until you realize you can easily introduce a 2 by multiplying and dividing by 2. Okay, so you have 2 times x times 2x minus 1. So this is our u, and this is our du. Now, what is this supposed to be? Because you can't integrate with two different variables under the same integral. Okay, so we have to turn x into u. We have to establish x as a function of u. Okay, so we have to solve for x in terms of u. So we define u equals 2x minus 1. So x, we have to solve for x like this. In terms of u, we get x equals u plus 1 over 2. So this is actually u plus 1 over 2. So we literally just turned an x in terms of u. And now, with everything in terms of u, we're now allowed to integrate. So 1/2 times u plus 1 over 2 times the square root of u du. Okay? Now, if we can bring out this 2 over here, let's bring this out, you get 1 over 4 times u plus 1 times square root of u du. Now let's distribute the square root of u so we can easily apply our inverse power rule. Okay, this is u to the 3/2 power plus u to the 1/2 power du. And as a result, if we apply the inverse power rule twice, you get 2/5 u to the 5/2 plus 2/3 u to the 3/2. Okay, plus c. And what we can do is do a little simplification. Okay. So this would be 2, this would be 1, this would be 1, and we get 1 over 10 u to the 5/2 plus 1 over 6 u to the 3/2 plus c. And if we were to substitute back in, we get 1/10, let's use radicals, times the square root of 2x minus 1 to the 5th power plus 1/6 times the square root of 2x minus 1 to the 3rd power, all that plus c. So with cases like this, you start with this tiny simple expression, and you can see we end up with a much more complicated expression because we had to express that lone x in terms of u. So let's do one more. In this one, sine squared of 3x times cosine of 3x dx. Okay? Now, let's rewrite this integral so that we can clearly see a good substitution. Now we have cosine and sine, but sine is sine is being squared. So it's most logical to let u equal sine of 3x. So if u equals sine of 3x, then du dx is 3 cosine of 3x. Or du is 3 cosine 3x dx. Right? So you have 3 cosine 3x dx. Now we have cosine of 3x times dx, but we just need a 3. But as we have done countless of times before, we can simply introduce a 3. Okay? So we have sine 3x squared times 3 cosine 3x dx. So here you can put in your u, and you have your du. So you have 1/3 integral, of u squared du. And that's 1/3 times u cubed over 3 plus c. So you have 1/9 u cubed plus c, and u is sine of 3x. So you have 1/9 sine cubed of x, sine cubed of 3x, u is sine of 3x, sine cubed of 3x plus c. Now there's one thing that's important about U-substitution when applying to definite integrals. So when you apply to definite integrals, then it's usually very helpful to convert the limits of integration as well. So let us try to evaluate the definite integral. Okay? So let's say we want to evaluate the definite integral of from 5 to 1, okay, from 1 to 5, of x over the square root of 2x minus 1 dx. So this is a definite integral, okay? So you might be tempted to use U-substitution, find the indefinite integral, put x back in, and if you put x back in, you would put these limits of integration and apply the first fundamental theorem. Okay? Now, what should we do? Okay, so what should we do? Now, let's have u equal 2x minus 1. If u equals 2x minus 1, du dx will be 2, or du will be 2 dx. So we can introduce a 2 by the 1. And now we have this lone x over here. So what is this x? So to find x, you solve for x in terms of u. So you have u plus 1 over 2. Now, if we make our substitution, you have 1/2 times this is du, 2 dx is du. So we have u plus 1 over 2 times du over the square root of u. Okay, so you have what looks like a very scary integral. So you look, yes, it does look like a very scary integral. However, what happened to our limits of integration? So here is where you have to account for the changes that occur with U-substitution. We cannot plug in 1 and 5 because 1 and 5 were the limits of integration for x. You can use 1 and 5 provided that once you take this indefinite integral, you put x back in, you sub in back for x, and you would then use the upper limit and lower limit 5 and 1. However, a better way to do this is to convert the limits of integration into u form, okay? Which is done by subbing in the x values to get the corresponding u values. So the lower limit 1, its u version will be 2 times 1 is 2 minus 1 is 1. So that stays the same. Okay? Now, the u version for this one, okay, that's 2 times 5 is 10, minus 1 is 9. So you have to change the limit of integration to 9, okay? So now that we changed our limits of integration, there is no need to convert back, okay? So I'll tell you what that means when we get to that spot. So let's take this to the front of the integral. So 1/4 times the definite integral from 1 to 9 of u plus 1 over square root of u du, which equals 1/4 times the definite integral from 1 to 9 of u to the negative 1/2 times u plus 1 du. Now distribute. Sorry, it's starting to look a little messy. Now this gets us u to the 1/2 plus u to the negative 1/2 du. And if we evaluate this integral, we get 2/3 u to the 3/2 power plus 2, okay, 1 over 1/2 times u to the 1/2 power. And now that we've changed our limits of integration, we do not have to back substitute. If we kept our original ones, we would have to back substitute and we would waste a lot of time doing computation. So we have 9 and we have 1. Those are limits of integration. So let's consider 9. This equals 1/4 times 2/3 times 9 to the 3/2. What is 9 to the 3/2? Well, that's 27. Okay, it's 27 plus 2 times u to the 1/2. Okay, so 9 to the 1/2, that's square root of 9, it's 3. So plus 6 minus 1 to the 3/2 power is just 1, minus 2/3 plus 1. Square root of 1 is 1. So what does that get us? So let's simplify as much as possible, okay? So this gets us 9. So if 2 times 9 is 18, plus 6 is 24. 24 minus 1 plus 2/3 is, that gets us 5/3. That gets us 5/3. And if we convert 24 into thirds, we have 72/3 minus 5/3 is equal to, that is equal to 60. This. So you get the, oh, wait a minute. Just picked up something. Thank God I caught this. It's 2. It's not, it's 2. Square root of 1 is 1 times 2 is 2. Okay, so we got 2. So thank God, notice in time. So we have 8/3. So you have 72/3 minus 8/3. That gets us 64/3. Okay, and we have 1/4 times 64/3. Cancel, cancel, 16. And we get 16/3. So our final answer is 16/3. So this, now you can see that integration is starting to get a little more intense. Okay, you can start to see that this integration is getting a lot more intense. Okay, you have a lot more of this substitution because they're now working with a lot more intense functions. What would happen if we had to evaluate from phi to 1? Okay, well, then we would have to evaluate. We took this alternate path. Then we have to evaluate 1/4 times 2/3 times the square root of 2x minus 1 to the 3rd power plus 2 times the square root of 2x minus 1 from 5 to 1. Okay, compare this with this. So this is usually easier. It's a lot more efficient. So it's usually efficient to convert the limits of integration to their U forms. Okay, and if you were to evaluate this, okay, you could do it in a very, and if you're good at it, at not making silly mistakes like I almost did, you would get 16/3 as well. Okay, so it doesn't matter if you convert the limits of integration, but be careful that if you do, then you have to stick with it. You don't want to convert back to x if you've already changed the limits of integration. Okay, nevertheless, you have to change the limit of integration if you're going to stay in U. So pick a lane and stay in it. Okay, now this was a pretty long lesson because this is one of the most important techniques in integration. We'll work more in refining this technique. If any of you have any questions about the video, okay, don't hesitate to comment in the video and I will do my best to answer. Please like this video and see you next time.